Very much. I hope that some conferences from now everybody will be able to pronounce the name of Chemnitz. First of all, I would like to say thank the organizers for not having to give this presentation during the German soccer game. So this was a good organization. My topic today is not vehicle localization like yesterday, but today I'm going to talk about situation assessment. I will start with a short motivation and an example application where it can be seen why we need situation assessment and how situation assessment is different from pure perception. And then the main part of the presentation will deal with the question, how can we do probabilistic situation assessment using uncertainties that we get from the tracking modules. And finally, I will show some results both from simulations and field tests. Okay. I think we are all aware of the fact that ADAS systems require sensor data that sense our environment, and that for that environmental perception we need tracking algorithms which detect entities in our environment and estimate their parameters, for example their positions, dynamic parameters and so on. Due to sensor noise, misdetections, fast detections, and other effects, normally we use probabilistic representations for this task. Most commonly an implementation of the Bayes filter, for example, Kalman, histogram, particle filter, whatever. If we now want to interpret what we have seen with the perception, we need something which is called a situation assessment, which means that we need to find the relations between the objects that we have seen. I think even today the most standard algorithm for this task are rule-based systems, so things like if the time to collision is below a certain value, then do something, neglecting any uncertainties. And here I would like to present a unified approach which also uses Bayes theorem in Bayesian networks for this situation assessment task. Okay. Before we go into theory, an application which demonstrates how we can use the situation assessment. Those of you who have attended the PhD forum may be familiar already with that. I repeat it nevertheless. What we have developed is an application on a test vehicle which aims at determining or aims at recommending a lateral maneuver to the driver. So imagine that we're on a highway or on a well-structured road. Then an idea could be to recommend to the driver if you should stay on his current lane or if you should do a lane change maneuver to the left or to the right. And this is exactly the objective of this specific application. At the moment, we are passing this recommendation to the driver via a human-machine interface, but you could also imagine to use this for highly automated driving. That is, the driver acknowledges a certain maneuver, and then this is executed automatically. This could be a vision for that. I have a short video which demonstrates that application. In that video you will see the camera images overlaid with the detected entities, in particular with the lane and the detected vehicles. And you will see the recommendation that is given to the driver encoded by this traffic sign over here. So keep lane, lane change left, lane change right. And what you see here is that at the beginning we have a vehicle overtaking us, and if this vehicle leaves our sensor field of view, then we get a recommendation lane change left because we have a vehicle in front of us which is within our safety margin. Now we don't do this lane change at the moment, we are waiting, and there's another vehicle coming from behind which changes this recommendation to keep lane, and this is the recommendation which is kept during the rest of the video, so to say. So this is just to get an impression what we are doing in the application. And what is behind here from an algorithmic point of view is that we have a perception of the environment, we have the lane information that we detected, we have vehicle estimates of the position and the velocity and so on. And what we want to do is to determine the relation between all those entities and to determine, can we now make a lane change maneuver or not? So this is what we want to do. And the challenge is that we do not exactly know where the lane is and where the objects are, but we only have estimates of that. We only have probability density functions. Okay, I don't want to go into detail concerning the functional structure. All I want to say with this slide is that we have sensors like cameras, radars, and ego motion sensors coming from the CAN bus. And this situation assessment block here receives probability density functions. On the one hand, it receives for each vehicle a Gaussian PDF, because we're using uncentered filters here inside. It receives a Gaussian PDF, and the state variables for the vehicles are its position and heading, velocity, acceleration, and yaw rate, so nothing special. And for the lane, which we have detected, we have 4 parameters: a curvature, a distortion, a lateral offset, and a width. So it is important to note here that we also get covariance matrices for these values, not only expectation values. And our task is now to combine these PDFs in order to create a recommendation to the driver. And we are doing this using a Bayesian network. Unfortunately, there's not enough time to introduce you to Bayesian networks. If you're interested in that, I would like to invite you to have a look in the paper. This is just a part of that network where we have a decision node capturing the 3 possible alternatives that we have, that are keep lane, lane change left, and lane change right. And we have different nodes which are influencing this decision. Those 3 are just a part of the network, it's not a complete one. So obviously the status of the lane influences our decision. So for example, if our own lane is occupied and the left lane is free, we may want to change the lane. So this is very briefly what happens here. So what we need to do is we need to determine the state of these nodes. So for each lane, we have to determine if it's dangerous, free, or occupied. The definition of these states is that the lane is considered dangerous if there's at least one vehicle inside this lane within a predefined safety margin. The lane is considered occupied if there is at least one vehicle in this lane, and the closest vehicle is outside the safety margin, but inside what we call a relevance margin, and the lane is considered free if there's either no vehicle or a vehicle very far away outside the relevance distance. And the task is now to determine this probability distribution of such a state using uncertain tracking information. Now, what we get from the tracking, once more, from the tracking modules, we get uncertain lane information and we get uncertain vehicle information. And this may lead to a representation like that we have expectation values and, for example, covariance matrices of the position. Now, if we have to decide if this lane here is free or not, then we run into some difficulties because we are not sure if this vehicle is on that line or on this lane, because the uncertainty makes it possible to have both. And we even don't know, is the vehicle inside the safety distance or not. So these are the things we have to decide here. And this is what I'm going to talk about in the next slides. So we can split the determination of the lane status into 2 questions. Is the vehicle on this lane, and is the vehicle inside my safety or relevance distance? So first of all, we could just start by calculating some lateral distance value for that. For example, we propose here to use something which is called normalized lateral position. So we have here a circle representation of our lane with some parameters, the curvature, a distortion angle, an offset, and the width. And what we can do is that if we have a vehicle which is around here, then we calculate the distance of this vehicle to the next lane border, and we normalize this distance by the width of the lane. If we do that and we have a vehicle that is exactly here, for example, we get an NLP of 0. Here we get an NLP of 1, and so on. So this is just a normalized lateral distance. So in a rule-based system, you would calculate that distance. You would say, if this is between 0 and 1, then I assume that the vehicle is on my lane, for example. Now, as I said several times, we have the problem that we don't know where the lane is and where the vehicle is. We only have estimates. And that's why we propose to use the uncentered transform. Probably most of you know that. This is a way to transform probability distributions in a nonlinear manner, or to approximate that this transformation. And we suggest that from the Gaussian PDFs that we have here for the vehicle and the lane, we calculate a new Gaussian PDF which gives us an expectation value for this lateral distance and additionally a variance. So actually what we do is we take this equation here and use it inside the uncentered transformation. That's it. And what we get is a one-dimensional Gaussian PDF for this normalized lateral position. If we have done that, then we can ask ourselves, how do we get a probability distribution for my lane association? This is the next step. And here we propose to construct a likelihood function. So if we want to use a Bayes theorem to determine this probability distribution, we have to define a likelihood function. So if we want to determine the probability that the vehicle is in a certain lane, given that I observe a certain lateral distance, then we have to determine it the other way around. So we have to define the likelihood that we observe a certain lateral position, given that the vehicle is in a certain lane. And that's what we can do here. We construct a likelihood function which is composed of a uniform distribution and Gaussian components here on the left and on the right. So for example, if we assume that the vehicle is in the ego lane, then we would probably assume an equal likelihood between the values 0 and 1 for this normalized lateral position. And we would here have on the borders a Gaussian component. And the width of this Gaussian component directly depends on the variance that we get from the uncentered transform. So if our perception modules give us a very low variance of this lateral position, then we would just have a rectangle function here. And if we have a very high uncertainty, this would be reflected in the result of the uncentered transform, and this would lead to a very broad likelihood function here. And from that, we can now calculate a probability distribution of the lane association of our vehicle. So we can say with a probability of 0.5, the vehicle is in my own lane. With a probability of 0.2, it's in the right neighbor lane, and so on. That's what we can do here now. And if the expectation value from the tracking stays the same, but the variance is changing, then this is directly reflected here in that situation assessment process. Okay, the second question was, how can we decide if the vehicle is inside a safety margin or not? Actually, this works quite similar. We have to define a distance value. We have used here a value which is called deceleration to safety time. I don't want to describe that in detail. Just imagine it's some kind of distance measure. And also for that, we use the uncentered transform to get a Gaussian PDF for this distance measure, and we define likelihood functions composed of a uniform distribution and Gaussian components to determine a probability distribution of that threat level. And now if we have done that, then we have for each vehicle a lane association distribution, and we have a probability distribution for the states inside my safety margin, between safety and relevance margin and outside the relevance margin, and then we can just combine those probabilities using some combinatorial equations that are explained more detailed in the paper. So this is one way of taking the results from the tracking modules, calculating probability distribution for one node in the Bayesian network, and to enter that distribution directly in the network. This is what is called soft evidence. So we calculate this distribution outside the Bayesian network and then enter it and do the inference to derive the decision. So there are some other ways what we can do in Bayesian network, but this paper focuses on the alternative of entering soft evidence into the network. Okay, if we do that, what happens? In order to investigate that question, we have performed simulations on the one hand, and we have tested the approach in a real vehicle and the real world. For the simulation, we have used a simple traffic simulator, which is called Scene Suite from our partner IEEE, which is, as usual, simulators able to generate sensor data and ground truth data. And what we have done is we generated a simple scenario where the red vehicle is overtaking us, so the blue vehicle is our ego vehicle. And we have taken the true lane and object parameters and added some artificial noise. And now what we have done is we have varied the amount of that noise. So we have varied the variance from the perception. And we have investigated how does this influence the situation assessment. So if we have a very precise environmental perception and a very uncertain one, how does this affect the situation assessment? And I can show you just some exemplary results of that. Let's, for example, consider this lane association. We have taken here a scenario where we have a vehicle just in front of us, which is in the middle of our ego lane. So for a rule-based system, it would be very easy to determine this is on my lane. And if we have low variances, then we see that we have here a probability for the vehicle being on our lane, which is 1, and the probability being on the left or right neighbor lane, which is 0. So here on the y-axis, you can see this lane probability. And what we have done here, we have increased the variance of the lateral object position. So we have, for example, assumed that we have another sensor which has much worse angular resolution or something like that. Whatever, we have investigated what happens if we increase the lateral variance. And what you can see here is that if the variance exceeds a certain value, then we are not so sure anymore if the vehicle is on the ego lane or not. For example, here we have only an 80% probability that the vehicle is on the ego lane, and we do have some probabilities which are non-zero that it is on our neighbor lanes. Again, the expectation value is unchanged, so the expectation value of the PDF is still in the middle of our ego lane, only the variance is increasing. And if we raise this variance to infinity, then we end up here at 0.2. If you're wondering why it's 0.2, it's because we are considering 5 lanes. So our ego lane and the 2 adjacent lanes. So that's why we end up by 1/5 probability if we raise the uncertainty to infinity. This is part 1, and a similar result can be obtained if we consider this threat level of the vehicle. So the question, is it inside our safety margin or inside our relevance margin? Again, we have considered the case where the vehicle is very far away, so we would normally not consider it relevant for us, which is reflected here by the fact that the probability for the lane being free is 1. And now we have again increased the variance, this time of the longitudinal object position. And now we find that here we are very sure that the lane is free. And if the variance increases, then we are not so sure. Then it could also happen that the vehicle is inside our relevance margin. So then here we have a period where free and occupied are equally likely. And then if we increase the uncertainty further, it is even possible to the system that the vehicle could be inside our safety margin. And this is why all probabilities end up here at 1/3. Now, if we consider this with real data in the real world, we could ask how does this influence our decision? So in a rule-based system, you would normally say, okay, if the vehicle is in my lane and the left lane is free, then do a lane change maneuver. So you would have sharp transitions. And what we have here is we see the utilities for each maneuver over time. So we have the 3 maneuver alternatives: keep lane, lane change left, lane change right. And normally, if we have no temporal filter behind it, then the decision alternative with the highest utility would be recommended to the driver. So what happens here is that we start at a high distance to the vehicle in front of us. So the utility of keep lane is the highest. And then we are slowly approaching the vehicle in front of us. And now the state of the vehicle is changing, the state of the lane is changing from free to occupied slowly, as we can see here. And this also makes the utilities for keep lane and lane change left change very slowly. And from this point in time here, we would recommend to the driver to start a lane change maneuver to the left, actually. And he does that, and after the vehicle crosses the lane border at this point in time, then suddenly the ego vehicle is one lane further to the left, and this is why the maneuver keep lane is now recommended. So this is just a glimpse on the results here, because I don't have the possibility to present them in all details. Okay. Actually, I'm coming closer to the end of my presentation. What I wanted to tell you in those short minutes is that we can use tracking uncertainties directly in Bayesian networks in order to influence our situation assessment. And we can do that by using adaptive likelihood functions, which are directly influenced by the tracking variances. In the next weeks, what we plan to do is that we also incorporate the existence probability of the vehicles into the situation assessment, because this is neglected now at the moment, because normally we don't even know if the vehicle exists at all, if it is there. So here, for these results, I've just taken vehicles which exceed a certain existence probability threshold, but I will take into account this explicitly in the next weeks. And before coming to the end, I would like to draw your attention to the fact that this is only one way of incorporating perception uncertainties into the situation assessment process. We could also construct adaptive likelihood nodes directly in the Bayesian network. And we could also ask the question the other way around. If we have knowledge about our situation, how can that influence our tracking? So we can ask the question in two directions. Okay, with this, I'm coming to the end of my presentation. Again, I would like to thank you, and I'm happy to take your questions.